So in force of interest, the idea is that the compounding is continuous. So until now, the kind of compoundings that we have studied, they were not continuous. They were happening at regular intervals. We started with the one that happened every year, compounding every year, whether it's compounding through interest or compounding through discount. And then we studied compounding quarterly, compounding monthly, compounding semi-annually. So monthly was happening every month. Semi-annually, it happens twice a year. Quarterly, it happens 4 times a year, right? But now we are into a situation where it happens continuously. And if the compounding happens continuously, then the interest that is involved is called force of interest, right? So if compounding happens continuously, then the interest involved or the interest rate involved is called force of interest. Okay. So here they explain that, you know, the symbol for I. So if you have I and superscript M with M written in parentheses, then it means you are having M compoundings per year. And if you let that M go to infinity, because that's what will happen if you let continuous compoundings, because if the interest is compounded continuously, then how many compoundings a year will there be? Infinite. Okay. So
it's kind of the interest that you use in the stock market, or which one?
Well, what is dangerous?
Well, that you have a period of time and you want to calculate how much is the effective interest in that period. How do you calculate it? Because it changes all the time and it's constantly.
So how is that related to continuous compounding?
I guess it happens continuously every day.
No, even if compounding is, that is not compounding, that is interest changing. So we're not talking about interest constantly changing. We're talking about how often it's being compounded under a given interest rate. So let's say the bank gives you that, okay, it's 5, the interest rate will be 5%. So you have to ask them that, okay, how often the compounding will take place. Normally by default, it's 5% per year, but it doesn't have to be. They can say it's 5% semi-annual, right? So what you are talking about is the interest rate changing. We're not talking about that. We're talking about how often the compounding happens. So if it happens semi-annually, then it means that right now, if you've deposited 100, the first time you will gain interest on it is 6 months from it. Okay. So there are different kinds of forces of interest that we will study. If the force of interest that is related to the usual compound interest, that's constant and that's denoted by delta. So if interest rate is constant, or let's say if the annual effective interest rate I is constant, and we know that it's compound interest, then the force of interest corresponding to it is interest corresponding to it delta is denoted by delta, and delta is equal to ln 1 plus I. And from here, can you find out I from this equation? I have delta is equal to ln 1 plus I. How will you find I from this equation? Huh? Take exponent of both sides. So I'll get e power delta is equal to 1 plus I. Yeah. So what would I be? E power delta minus 1. So these two are nice equations where you can interchange between I and delta. And delta is equal to ln 1 plus I, and I is equal to e power delta minus 1. So now this is for the constant force of interest, which happens when the compounding is when we have compound interest, then the force of interest corresponding to it is constant. But in general, the force of interest doesn't have to be constant. So in general, we mean that the interest rate doesn't have to be compound interest. So in general, the force of interest is denoted by delta subscript T and is given by delta T is equal to A prime T over AT, where A of T is the accumulated amount at time T. So for example, if I is the annual simple interest, simple interest rate, then what is A? P times 1 plus IT, right? In case of simple interest, we know that it's P, the amount, accumulated amount is 1 plus IT. That's the accumulated amount at time T. So let's calculate force of interest in this case. Delta T is equal to a prime t over at. So what's the derivative of this expression a of t? Remember, p is a constant, I is a constant. So what will be the derivative of a? I or pi?
Oh, pi.
Yeah, because you keep this constant p, that's a multiplied constant, and the derivative of 1 is 0, and the derivative of it is I with respect to t. So pi, and divide by a of t, which is p times 1 plus it. So the p's cancel, and so it's equal to I over 1 plus it. So that's the force of interest in case of simple interest. Okay. So let's see. We are in a position to do the problems. Let's look at problem 10.1. Okay. A deposit of 500 is invested at time 5 years. The constant force of interest is 6%. Determine the accumulated value of the investment at time 10 years. So let's first develop a handy formula. So we know that in case of for compound interest, a of t is equal to principal 1 plus I power t. And we want to get an expression which involves the force of interest instead. So what was the relationship between, so we have this expression, I is equal to e to the delta minus 1, or we can also say 1 plus I is equal to e to the delta, isn't it? So here, replace 1 plus I with e to the delta is equal to p e to the delta t. So if you have the annual compound interest, you will use this expression. If you have the force of interest under continuous compounding, you will use this expression. Okay, so then 10.1, we want the accumulated value, and we are given the force of interest. A of t is equal to p e to the delta t. P is 500, e to the delta is 0.06, and t is 10 years. So what do we get? Don't want to say it loud?
I got $900.
Doesn't that look too much?
No,
6.
it's time 5 years. You use 10.
Oh, it's invested for 5 years. Oh, what is this? A deposit of 500 is invested at, it's deposited at time 5 years. And then what's the value after 10 years? So it sits for 5 years, right? Because it's deposited at time 5 and then it's collected at time 10. So it sits for 5 years and not 10 years. So what do we have? So this is a situation in the time diagram. The deposit happens at time 5. And you want to know its value at time 10. So it sits around for 5 years, right? Okay. Let's look at 3. Assume that the force of interest varies with time and is given by delta t is equal to a plus b over t. Find formula for the accumulation of 1 unit money from time t1 to t2. Okay. I think no, but let's leave this one. Let's get more comfortable with the idea first before getting into this kind of problem. Let's look at 4 first. 10.4. Okay. You need 500 on January 1, 2012. To save for this amount, you invest X on January 1, 2008 and 2X on July 1, 2008. The force of interest is this one on January 1, 2008. Find X. All right. So let's draw the time diagram. So which one do you want to take as time 0?
January 1st, 2008.
Okay. January 1st, 2008. All right, because that's when you make your first investment. Okay. And what do you deposit then? You invest X at that time, right? X at that time. And then you invest another 2X on July 1. So what would be the time on July 1? On January 1, 2008, time is 0. What will it be in July 1, 2008? If we're counting it in years.
0.5.
Half a year, right? 0.5.
So by July is 7.
No, July is the 7th month, but July 1 means you've just finished 6 months. You've just finished June 30, which means you've just finished half a year. So 2X comes in at t is equal to 0.5. Okay. And you want both of these to accumulate. So what's our final time? January 1, 2012 is how much? T is equal to? 4 years. Okay. So now we had that formula in case of constant force of interest P E delta T. Now, if the force of interest is not constant, so if the force of interest is delta subscript T, means it's not constant, it now depends on time, then the amount at time T is equal to P e power 0 to T delta T dt. Now, this is not a mathematically correct way of writing it. Mathematicians will frown at this, because what mathematicians want is, if T is in the limits, then you want some other variable here. They would try to write it as delta subscript R dr, but it doesn't change anything. Even if you don't do that, and if you keep this as T and this as T, you just can't go wrong in your calculations. It's just not considered very polite to write it like this. Yeah, mathematicians get offended, but that's okay. All right. So in this case, so again, like in that other problem where there was 100 coming in at some time and then a 200 coming in at some time, we're considering that 100 separately and seeing what happens to it, and then the other one separately and add them together. So let's consider this X separately. This X was being deposited at time 0. So what happens to this X? That's like the principal, isn't it? Or let's even separate it out. The initial deposit X grows to, X is the principal, so it'd be principal times e power 0 to, how many years does it sit? No, doesn't it sit the entire 4 years? It's deposited here, and we are interested in what's happening at the end, right?
Yeah.
At time 4, because you need 500 at time 4. So this grows to, the initial deposit X grows to, in 4 years, E be 0 to 4 and delta T dt.
Delta dt is 0.02.
Right. Now we'll substitute what delta T is. That's 0.2T, 0.02T. So what's the integral of 0.02T? 0.02T squared by 2. 0.01 T squared would be 16. X e to the 0.16. So this is what happens to that initial X after 4 years. It grows to this much. And now do the same thing with the deposit 2X grows to now. you may be tempted to say that, okay, this 2x sits for 3.5 years because it comes in here at half a year and we collect it at time 4. Yes, it sits for 3.5 years, but we can't say that it goes from time 0 to time 3.5 because it's obviously going from time 0.5 to time 4. So what will happen is that when we write the expression for this, 2x is the principal. Remember, we are trying to use this equation. 2x is the principal. And now this is the normal equation because normally your principal is being deposited at time 0 and it stays for time t. So you go from 0 to t. This one is deposited at time 0.5. So 0 in this case is 0.5. And it sits up to time 4. So this would be integral from 0.5 to 4, right? E power integral of 0.5 to 4 instead of 0 to 4 like we did in the first part. And again 0.02 t dt. .01 t square from 0.5 to 4. 0.01 will be 16 minus 0.5 squared. So what would this be? 0.16 minus 0.0025. So 0.1575. Right?
So those equals are equal to A of something, A of t.
So do we agree that this first x grows to this much, xe 0.16, and the second 2x grows to this much after 4 years? And what do we want? We need a total of 500 after 4 years. So basically that 500 should equal this one plus this one.
One question.
Yeah.
Whenever you have the formula, is A of t equal to x times e to the power of.
So the generic formula in case of force of interest is this one. A of t is equal to p e power integral 0 to t of delta t dt. But we have to understand that this 0 may not always be 0. We may be depositing at some other time and then that time kicks in over here, right?
Right. My question is from the notation,
Uh-huh.
A parenthesis t. So you put the t is being 4 or 0.4?
Yeah, so the A of t is the amount at time t. So this is the formula for amount at time t. So right now, this one is what x grows up at time 4.
So
This one is what 2x grows at time 4. And so the total accumulation at time 4 is this plus this, and that we want to be equal to 500. Yeah, that's why I didn't write any A's for these because there were 2 of them going on and it would have been confusing. What would you call it? Like A1, and then that A1 has a different principal, A2 has a different principal, and even their deposit times are different. So that's why I just said in words. Okay. So now, can we calculate x from this equation? Yeah, what is it? I mean, this looks like confusing, looks like too many variables, but e to the 0.16 is a number, right? Similarly, this is a number. So after, in fact, we can even factor out the x. E to the 0.16 plus 2e to the 0.1575. And then you can put it all in one stroke in the calculator. You do 500 divided by e to the 0.16 plus 2e to the And you know that when you put it in calculator, you need a bunch of parentheses, one around the whole denominator, one around the power of the phi. So what do we get in the end for x?
I got 142.26.
142.26. Makes sense. Because, okay, let's understand what's going on practically. I need 500 4 years from now. And I want to put x now and 2x 6 months from now. Which means whatever I put now, I want to put the double of that 6 months from now. And I want the whole thing to grow to 500. So what am I doing practically? I'm putting $142. Let's forget about the 26 cents. That to keep it simple. So I'm putting $142 now. And in 6 months, how much will I put? $284, twice of 142. So it makes sense that 142 now and 284 6 months from now. How much have I put total? 400 something. So it makes sense that that kind of thing should grow to 500. Okay. Oh, what was that? I'm recording and it signs me out. But I guess it's still running, isn't it? Because this thing is still there and it says screen sharing. So let's hope it's still going. All right.
So these videos, are you gonna post them and can we hear you talking whenever you?
Yeah, I plan to post this one. Yeah. Let's hope it turns out good. Okay. Let's look at number 7. Bruce deposits 100 into a bank account. His account is credited at a nominal rate of interest I convertible semi-annually. See, that's what I was mentioning, that those semi-annual rates and everything that we spent before, they will keep on reappearing. So we'll have more and more practice of that. At the same time, Peter deposits 100 in a separate account. Peter's account is force of interest, delta. After 7.25 years, the value of each account is 200. Calculate I minus delta. Good problem. Okay, so let's see. So let's focus on Bruce first. So Bruce deposits 100. So what is the time at which we are interested eventually? 7.25 years. So after 7.25 years, Bruce has how much?
200.
Okay, 200. And what is that in terms of the principal and the rate? So 100 is his principal, and its nominal rate of interest I converted semi-annually. So normally, if it was annual, then it would be 1 plus I, but now it says it's converted semi-annually, so it'd be I by 2. And how many semi-annual periods are there?
2 times 7.25.
2 times 7.25, right? 2 times 7.25. And what will we get from this equation? I. So let's see. How do we get I? So we divide by 100. 14.5, and then take the 14.5th root. 1 over 14.5. So what do we get for I in the end? 9.8%. Okay. So this is the business we did with Bruce. Then let's take care of Peter. So what's the equation for Peter? At the same time, Peter deposits 100 like at the same time as Bruce, but Peter has force of, now this is a constant force of interest. So what's the equation for constant force of interest? A is equal to PE delta T. So what numbers go in? What is A? 200 again. P is also 100. And E power delta is unknown. And time is 7.25. And from this equation, we will calculate delta. Two is equal to E power 7.25 delta. And how do we get delta from here? Pre-calculus. ln. Take ln of both sides. ln2. 7.25 delta. Delta is equal to ln2 divided by 7.25 equals. Yeah. So 9.56%. So we were to calculate I minus delta. I was 9.8% minus 9.656% is equal to 0.24%.
What was the question?
Find I minus delta.
Gotcha.
Okay. So let's see.
What does it mean, that subtraction? Does it mean anything in reality?
Oh, yeah, this one is more kind of an abstract situation because I was Bruce's nominal rate semi-annual and the delta was the force of interest for Peter. So subtracting the two, okay, one thing which we can say is that okay, everything was the same for both. They deposited the same amount and they collected the same amount. They both deposited 100 and they both collected 200 after 7.25 years. So one of them had a interest rate that was convertible twice a year. The other had a continuous one. So what we are seeing is that the one who had convertible twice a year, it needs to be a little bit higher compared to the other one in order to be equivalent.
So Bruce made more money than Peter. In the same
If they were the same, so like one of the semi-annual one turned out to be 9.8%, the other one turned out to be 9.56%. So it means even though Peter's rate was lower, 0.25 lower, that was still equivalent to the other one because the compounding was happening more frequently. It was happening infinitely. So if more compounding happens, then a lower interest rate actually matches a higher one with less compoundings.
So the 9.56 is happening all the time 4, 7,
Yeah,
25
that's
years.
continuous compounding. Yes, it's happening throughout, whereas the 9.8 was happening only twice a year. And so basically, I know that even if I'm 0.24 less than your rate of 9.8%, I'm still going to catch up after this many years. Okay. So now I will put the homework. Next homework is due on the coming Monday. And I think now in the foreseeable future, I see like meeting face to face every day, except if something happens to me or to campus. Yeah, you never know in this day and age what may happen. All right.